Okay, let's dive into this. Welcome to today's Explainer. Whenever we hear some flashy statistic on the news or read a new study about what people are buying, thinking, or doing, we rarely stop to ask the absolute most fundamental question. How did they actually get that information? Statistical analysis is completely impossible without data. It's the raw material, literally the lifeblood of statistics. But getting your hands on that raw material requires a highly systematic process. So today, we're looking at the crucial first step of any statistical inquiry, figuring out how to actually collect the data. We're going to compare the two major heavyweights in the data collection world to see exactly how researchers figure out the truth about the world around us.
Here is our roadmap for today's Explainer. First, the data collection dilemma. 2, the census method. 3, limitations of the census. 4, the sampling method. 5, the risk of bias. And finally, 6, making the right choice. All right, let's jump straight into Section 1, the data collection dilemma. Every investigator faces a massive hurdle right out of the gate. How on earth do you measure a massive group? Well, to solve this dilemma, we first have to agree on our terms. And what's really interesting about this slide is that in statistics, a population probably doesn't mean what you think it means. It doesn't just mean a group of human beings living in a city. In statistics, a population, or universe, as it's sometimes called, is the totality of all persons, objects, or items relating to your specific inquiry. So, if you want to know about the quality of light bulbs rolling off an assembly line, the population is every single light bulb produced. Your population is simply the entire universe of whatever specific thing you happen to be investigating. Moving right along to Section 2, the census method. So, once you have your population defined, how do you actually gather the data? Well, the mechanics of the census method are incredibly straightforward, though definitely not easy. In a census inquiry, you collect data from each and every single unit constituting the population. There is absolutely no guessing here. If your population is 100 items, you physically check all 100 items. You enumerate absolutely all items in your universe, leaving no stone unturned. And because you're leaving absolutely nothing out, this method has some incredible merits. First and foremost, the data you collect is highly accurate and highly reliable. You are surveying everything, so it is fundamentally less biased. You also get this amazing added bonus of gathering extensive information about totally diverse characteristics all at once. A perfect real-world example of this is the Census of India. By literally surveying the entire population of the country, the government doesn't just get a simple head count. They get these exhaustive, diverse details on age, sex composition, occupations, rural-urban breakups, and education levels, all in one massive sweep. The information is direct, and the reliability is just unmatched. But that brings us to Section 3, limitations of the census. As you can probably imagine, we can't just use a census for every single question we have. While the census method is definitely the gold standard for accuracy, its practical demerits are pretty severe. It is a very, very costly proposition. It's incredibly time-consuming to execute. Furthermore, you can't just do it alone. You need a massive team of trained, reliable enumerators out in the field doing all that counting. And the crucial point is, because of the vast amount of money, time, and energy required, this method is realistically restricted mainly to governments or giant institutions. Average researchers simply do not have the budgets or the workforce to pull off a true census. Which leaves us with a very real problem. What do you do if your population is massive, but you only have a tight budget, limited time, and just yourself or a tiny team to do the research? That leads us nicely into Section 4, the sampling method. To solve that massive resource drain, we rely on a completely brilliant scientific workaround. Instead of exhaustively testing every single item in the universe, the sampling method relies on, you guessed it, a sample. A sample is simply a small, selected, representative part of the population. Under this method, the investigator studies just this small group, and based on what they find, they draw educated inferences for the entire universe. Essentially, you study the part to make conclusions about the whole. And this brilliantly illustrates the exact difference between the two techniques side by side. Imagine you want to find out the average monthly expenditure on a specific brand of cold drink by the students in a large school. If you use the census method on the left, you literally have to track down and collect data from each and every one of the 2,000 students. That sounds exhausting, right? But if you use the sampling method on the right, you might just select a few representative students from each class. You collect data from that small handful, and then use those averages to represent the entire 2,000 student population. The reasons this method is so widely used today are entirely practical. Sampling is highly economical, saving you massive amounts of money compared to a full census. It is incredibly time-saving, it's highly convenient, and in many ways, it's actually considered more scientific because of the complex methodology used to select the sample. Ultimately, the sampling method is the ideal choice when the population size is huge and the items within it are broadly similar to each other. It is without a doubt the practical hero for everyday researchers and scientists. But, of course, there is a catch. Let's look at Section 5, the risk of bias. No statistical method is completely flawless. The major demerit of the sampling method relies entirely on human error. If the selected units aren't truly representative of the whole population, your entire study just falls apart. This is the potential risk of biased sample selection. Think back to our cold drink example for a second. If you accidentally only sample students who happen to be on the track team, their thirst and cold drink expenditure might be way higher than the average student, right? Your sample is biased, and that leads you to draw completely wrong, inaccurate conclusions for the entire 2,000-person universe. If the sample is wrong, the data is basically useless.
Let's wrap things up with Section 6, making the right choice.
So, as an investigator heading out into the field, how do you actually choose between these two techniques? Let's move to and see how this builds out in our summary table. If we look at accuracy, the census is highly accurate and reliable, whereas sampling always carries that inherent risk of bias. When it comes to cost and time, the census is incredibly costly and time-consuming, while sampling is highly economical and fast. In terms of execution, a census demands a massive team of enumerators, whereas sampling is convenient and can be executed scientifically by a much smaller team. Ultimately, this tells us exactly who these methods are best for. The census is built for governments and massive budgets, while sampling is the absolute go-to for investigating large populations on tighter budgets. Which leaves us with something pretty fascinating to think about long after this explainer ends. Because a true census is so incredibly rare, that means nearly all of the data, the statistics, and the studies we consume on the news every single day rely entirely on the sampling method. So the very next time you see a statistic, you have to ask yourself, who selected that small sample of people, and is there any chance they were biased? Because knowing how the data was collected is absolutely just as important as the data itself. Thanks for joining me on this explainer, and keep questioning the data.